Okay, so what if I told you there's a way to slash your LLM API cost by up to 90%? And I think not a lot of developers are taking advantage of this. Even as models become more powerful and context length grows, cost can still skyrocket as the usage goes higher. This is where the concept of context caching comes into play. This technique not only reduces API calls and saves money, but it can also act as an alternative to retrieval augmented generation for smaller set of documents, avoiding the overhead of vector stores and indexing and storage. Major API providers like OpenAI, Anthropic, and Google have implemented context caching. Google was in fact the first one to introduce this, but they initially required 32,000 tokens to cache. Now, they have lowered this to only 4,000 tokens, making it even more accessible. So in this video, I'm going to show you how to get started with Google's implementation of context caching, how it works, and how you can build new systems that can learn using context caching. In this video, I'm using Google's context caching implementation because it gives you a lot more control compared to the implementation by Anthropic and OpenAI. I have a video on how to use context caching or prompt caching with Claude. If you're interested, link is going to be in the description. Context caching is extremely helpful if you're working with large documents such as large PDF files or video files, and the user is going to be interacting with those files repeatedly. So you can cache these files once at a much reduced cost, and then you can let the user interact with those cached files. This will both help with speed plus cost decrease. According to Google, you can choose how long you want to cache to exist before the tokens are automatically deleted. By default, time to live is going to be 1 hour, but you can set it to a few seconds if you want. I think in certain cases, context caching can be used as a replacement to a retrieval augmented generation, especially you don't have to deal with vector stores and extra cost of the pre-processing and embeddings. So in cases where you have relatively smaller documents and the user is interacting with those documents for a short period of time, you could potentially use context caching. Beyond RAG, you can also use this for in-context learning, where you add information about a new library and Gemini will be able to look at that documentation and use it in subsequent calls. I'll show you an example later in the video. But before that, cost is the primary driver for caching. So let's see how much cost reduction you can expect. Well, for Gemini 2.5 Pro, there are different pricing for the number of tokens you're using beyond 200,000. But in general, if you cache your prompts or your tokens, you're going to be looking at about 75% cost reduction compared to non-cached tokens. And this works across the board for multimodal tokens as well as text-based tokens. For Gemini 2.0 Flash, it's very similar. For Gemini 2.5 Flash, context caching is not available yet. They're saying it's coming soon. But there is additional storage cost, which they are measuring in terms of number of tokens stored per hour. So therefore, the bigger Pro version, there's $4.5 per million tokens per hour. So it's very important to consider that storage cost and for how long you want to keep those tokens. First, let me walk you through how context caching works, and then we're going to look at a practical example where we're going to use it in context learning, where we're going to provide documentation of the MCP's Python package, and we're going to ask Gemini to create new MCPs for us. So first we need to install the Google Generative AI package. We import all the relevant packages that we will need. And here we're just starting Gemini client. In this example, I'm going to be using this fight plan, which is about 600 pages long. And as you can see, it's a scanned document. The good thing is Gemini can process multimodal information. So using the vision capabilities, it will still be able to understand this scanned document. First, we are going to provide a URL of that document. Then we will extract the document, and then we're going to upload that document through our client that we created. So basically, we are storing the document on Google Cloud. For this example, we'll be using Gemini 2.0 Flash. 2.5 Flash does not support context caching yet. And the system instruction is extremely simple. You are an expert. Here's how you create a cache. So you provide the model name by using the create cache function. In configurations, you can provide any system instructions that you have, and then the contents that you want to cache. In some cases, if you have very long system instructions, you can just cache those system instructions or along with different documents that you want to use in subsequent calls to your model. Here, I actually made a mistake. I provided my Grok API key instead of Google API key. So we're going to run everything again just to make sure we're able to upload the document. And now it's creating the cache for us. This process can take a few seconds, but once the process is complete, we should be able to see our cache, and there should be a URL that tells us where exactly the cache is stored. So here, the total number of tokens that are stored are about 160,000. So the cache is created, and now we can interact with this cache just like we will interact with a normal Gemini model through the Gemini API. Here, we're going to use that cache in our subsequent requests. The way you do it is you provide a configuration where we're going to point it to the cached contents. You can have multiple different cached at the same time. So we just need to provide that configuration and then the user request. Before showing you the final response from the model, we can look at some of the metadata that was used. And this is really helpful in understanding what exactly happened inside. So there were a total of 9 tokens in our request. The cached number of tokens are here. And then the total number of tokens that were processed by the model are this. So basically adding the cache tokens plus the input tokens. And I think it generated a total of 553 tokens. So if you add everything together, we are going to be seeing around 160,000 tokens. The model does not differentiate between the cache tokens versus non-cache tokens. So the model is going to process them exactly in the same manner. And here's a response that was generated by the model as a concise summary of the transcript that was provided, right? So a really concise summary of that 600 pages document. Before showing you how to use caching for in-context learning, let's look at a couple of very helpful functions or techniques. First, since you can have multiple cache, so you can just iterate through those cache and list all the caches that are available. Second, which I think is going to be extremely helpful, is if you want to update your cache. So by default, if you don't provide time to live, it's going to cache the contents for 1 hour. But you can dynamically update the cache duration. So for example, here we are just setting it to 300 now. And that's going to update our cache duration to 300 seconds. But then let's say you want to delete your cache after a user session expires. So you can just use the delete function on the cache to completely delete that cache as well. In the rest of the video, we're going to be using this example from Philippe, who is part of the Google DeepMind AI developer experience team. And he has a really awesome example where he is caching the contents of a GitHub repo related to MCPs, and then using that cache contents, he's using Gemini model to create subsequent MCP servers. And the cache contents is going to cost us around 31 cents instead of $1.25 per million tokens. So I'll use his code in the same notebook, but I am going to put a link to the original notebook that he put together. First, we need to install the git ingest package. If you haven't used this before, this is a very awesome package. Basically, it will let you convert any GitHub repo into LLM ready markdown files where you can just convert the whole GitHub repo into LLM ready document. I have used the web version, but I wasn't aware that there is even Python package. So let's say if you go to any GitHub repo and you replace the GitHub with git ingest, then you're going to see that it's going to take you to this new web interface for git ingest. Here you can define which type of files you want to include or exclude, and it will create a single file with all the contents, which is pretty amazing. And then you can feed these files or this single file into an LLM, and it's going to have all the context of a complete GitHub repo. I have been using that a lot, but I did not know that there is even a Python package. Now, to set it up, we're going to create another client for our Gemini models. In this case, we're going to be using the 2.5 Pro. Here is a system instruction. And the idea is that we're going to provide contents of the fastMCP GitHub repo, and we'll let Gemini create MCP servers based on its contents. A fastMCP is a Python package that lets you create MCP servers. So they have really good documentation on how to get started and how to set up your own MCP servers. Now, the system instruction in this case is going to be your helpful coding assistant with a fastMCP GitHub repo available in context. If a user asks question about fastMCP or how to build an MCP server, use the available information. And we're going to just ingest everything from this repo except the JSON files, CSS, JS, and some of the other files or file types related to virtual environments, GitHub, etc. Now, as I said, I wasn't aware of this Python package, but I think I'm going to be using it a lot more now. Now, we can look at what exactly we get as the output. So I think there are estimated close to 130,000 tokens in here. If we look at the tree, I guess this is going to have the structure of the repo, and then it has the content, which is going to be the actual content of our repo. Next, we're going to create our cache. The way we do it is, again, we'll just use the create cache function on the client. Then we use our model. We'll also provide the contents, just like the way we did it for the PDF file, along with our system instruction. So all of this is going to be cached. And in this case, we already have 300 seconds time to live. So the cache is going to be automatically deleted after 300 seconds. So we have about 154,000 tokens that are cached. And you can imagine having a 75% cost reduction is very significant if you have about 150,000 tokens. Now, after that, we can just interact with this cached content the way we would normally do with your system prompt and your context. So we're going to use the normal API client. Let's say the prompt is build a simple MCP server for reading and writing local files under temp MCP. We'll just need to provide the name of the cache. And after that, we can look at some of the metadata. So about 154,000 tokens or 55,000 tokens were cached. 18 tokens are not cached. These are the tokens from the input. Then there are tokens for the thought, which are not cached. And then we have a smaller number of output tokens, which again are not cached, right? But the vast majority of tokens are cached, and hence we're going to be paying a substantially reduced amount for these tokens. Let's look at what exactly it did in the response. So it says, here is a simple fastMCP server that allows the reading and writing files within a specific directory. So it created an MCP server. Let's see, it has resources which are needed for the MCP server. And then it also needs to add those tools. So you can actually see, yeah, it created a tool for writing files. Then I think there's going to be a tool for reading files as well. And then here's how exactly you can run the code along with the exact explanation of how the code is implemented. And Gemini has no idea about MCPs, but looking at the cached content, it's able to come up with an implementation. So I'm not going to test it out. I'll probably create another video, but I do have a video on MCP servers and how MCPs are different than normal function callings. So I'm going to put a link to that video. Make sure to watch that if you're interested in the topic. So this was a quick example of what context caching is and how to get started. Google is not the only one. Anthropic also has implementation of content caching, which they're calling prompt caching. Even OpenAI has their own implementation. I have created a couple of videos on those, but what I have seen is that Google provides you a lot more control compared to OpenAI and Anthropic. So it's a very important concept that you need to learn if you're using any LLMs through the APIs. It will substantially reduce your cost, and in some cases, it can also help you reduce latency. Now, if you like technical contents like this, make sure to subscribe to the channel. I hope you found this video useful. Thanks for watching, and as always, see you in the next one.